Vertex-Edge graphs and adjacency matrices are a great way to organize data and figure out logistics in particular situations. So let's just jump right in. Alphabet Airlines offers service to 7 U.S. cities. Obviously, I made this up because, well, A, B, C, D, E, F, G. There you go. You can look and see the first letter of the cities. Atlanta has flights to and from Boston, Chicago, and Erie. Boston has flights to and from Atlanta and Denver, and we can read all that. But then the first thing says, draw a vertex-edge graph. So that's actually what we're going to do, well, first. So every city starts with a different letter. It's planned that way. I'm going to just put A, B, C, D, E, F, G around here. They are not going to be in a proper geographical location, because Denver is actually not to the east of Atlanta, it's to the west, but whatever. Yeah, Fairbanks, Alaska would not be that far south. And Greensboro is not south of Atlanta. Okay, but we're going to read through this and we're going to connect them where appropriate. So Atlanta has flights to and from Boston, Chicago, and Erie. So Atlanta to Boston. We'll switch colors just so things don't all run together. Atlanta to Boston, there's that. Atlanta to Chicago, and Atlanta to Erie, Pennsylvania. There we go. And so far we have connected Atlanta to the 3 cities that it is connected to. And it did say to and from, so I can go from Atlanta to Boston or Boston to Atlanta. All right, let's keep reading. Boston has flights to and from Atlanta. That's already taken care of. And Denver. So we're going to connect Boston and Denver. And when we do, it connects. We do this. We could swing it around this way, but I do want to point out something that confused me the first time I saw this, and it's that dot right there, where this path crosses that path. It means nothing, okay? This is just an airplane that goes this way and an airplane that goes this way, and hopefully they don't meet right there, but that's the path where they would both cross. It means nothing. It really means nothing in a mathematical context. I would look at these points of intersection and think, oh, is that important? It's not. Okay, Chicago has flights to and from Atlanta. Done. Fairbanks and Greensboro. Okay, so let's just pause right here and talk about what we see so far. We are connecting cities using airline as an example. And I just want to point out that Atlanta offers flights to 3 different places. 1, 2, 3. Boston has flights to 2 different places. Chicago has flights to 3. We can't talk about the rest yet. We haven't completely filled in everything we need to fill in. But we do know that much so far. And what I just said is actually going to be really important when we talk about the degree of a vertex, when we define vertex too. Denver has flights to and from Boston and Greensboro. That's convenient if you ever want to go to Denver from Greensboro. All right, Erie has flights to and from Atlanta. Chicago, Fairbanks are connected. That's done. Greensboro has flights to and from Chicago and Denver, and we are done. So list each vertex. Well, what's a vertex? Well, I'm glad you asked. It's in this case, it's like a corner point. But I'm just going to list them. So A, B, C, D, E, F, and G. And then it says list all of the edges. And so I'm going to just show every connection. And all the connections in this case are airplane flights. So all of the edges, that would be like AB. Now, could you put BA? Yeah, you could in this case. You could. AB's, BA, same thing. So AB is a thing. AC is a thing. AE is a thing. I'm going to do this systematically. So we are starting with Atlanta and just going through there. And then we'll just go to Boston. And Boston to Atlanta has already been taken care of in a different order, but it's okay. And then Boston to Denver has not been written, so BD is an edge. By the way, the edges are what I drew in red. All right, let's go to Chicago. Chicago to Atlanta has been taken care of, but Chicago to Fairbanks, Chicago to Greensboro. All right, we'll go to Denver. D to B is good. See, we have it, not in the same order, but D to G has not been talked about yet. We go to E, and E connects to A, that's taken care of. F connects to C, that's taken care of. G connects to D, G connects to C. Those are both taken care of. So we have 1, 2, 3, 4, 5, 6, 7 different edges, which are basically 7 different flights. And then it says, what is the degree of each vertex? Well, the degree of a vertex is basically, in this case, the number of flights that come out of that vertex. So A, the degree of A is 3. The degree of B is 2. 2 because I have 3 flights coming out of A, I have 2 flights coming out of B, I have 3 flights coming out of C. Now, oops, 3, not 2. I do want to point out that I'm saying A equals 3. The degree of A is 3. A itself doesn't equal 3. Atlanta doesn't equal 3, but the degree of A is 3. So you don't have to write it with an equal sign. Sometimes you can write it with a colon. You can just write it as a sentence. The degree of A is whatever. All right, D. The degree of D is 2. See, 2 flights. The degree of E is 1. The degree of F is 1. And the degree of G is 2. And then it says, list all of the vertices adjacent to C. So every vertex, well, it's a vertex. We haven't even talked about what the exact definition of a vertex is, but I think it's obvious from the context that this is a vertex and this is a vertex. So in this context, a vertex is a city. So list all the vertices adjacent. What's adjacent? Well, I would say adjacent normally means beside, like, you know, my finger and my ink pen are adjacent to each other, but in this context, it really means connected, and we're going to really flesh those definitions out in a minute. But basically, all the cities that are connected to Chicago, so Atlanta, Greensboro, and Fairbanks. So Atlanta, I'll put them in alphabetical order. It doesn't matter, though. A, F, and G. And then write the adjacency matrix. What? Okay, now things get really fun, and this can really get sloppy if we're not careful. And there's going to be a lot of sliding up and down on this. And actually, to avoid all the sliding down, sliding up, sliding down, sliding up, I'm going to put the answer for the adjacency matrix up here beside my graph. If you have room, I recommend you do the same. So here we go. We are going to create a matrix that represents the paths that we can take, well, the edges on this vertex. And it's going to have 1, 2, 3, 4, 5, 6, 7 rows and 7 columns. So A, B, C, D, E, F, Greensboro. All right, there's that. And then the columns. A, B, C, D, E, F, Greensboro. All right, there is going to be a lot of room for error if we don't draw some straight lines. So I'm going to take just a minute and draw some lines just to make sure that I keep everything straight here. It's going to be very helpful that I do this. So that we're going to have that one. We're going to have that one, that, and that, and that. This might be super boring for you to watch me draw straight lines with a ruler, but it's just going to help me organize the data. With a matrix this large, it's going to be really easy to just have all kinds of crookedness and not really even be able to tell where we're going. So I find it beneficial to do this. Okay, I've said this before with adjacency matrices in a different context, but the row is where we're coming from and the column is where we're going to. Okay, so here we go. We are going to start from here and go to here. And it really starts with a tricky one. And we'll just see where we go. So Atlanta to Atlanta. Can I go from Atlanta to Atlanta? And you're probably like, well, I'm already there. And I agree. But here's the real idea. I'm not going from Atlanta to Atlanta because I'm already in Atlanta. But the really big idea is this. My graph doesn't have a little A with a path that loops around to it. It's not looping back around. Like, you're not going to get in an airplane and fly, look over the airport, and then land back in Atlanta. That's not going to happen. So this one is a 0. 0 meaning there are 0 flights from Atlanta to Atlanta. There is 1 flight from Atlanta to Boston. So from A to B, there is 1 flight. From A to C, there is 1 flight. From A to D, there are 0 flights. From A to E, there is 1 flight. From A to F, there are 0. From A to G, there are 0. Okay. There are some fantastic patterns that we can point out here, but let's not yet. Let's actually go ahead and keep filling this out. Can I go from Boston to Atlanta? Well, yes, I can. There is 1 flight that helps me do that. Now, I keep saying there is one flight. So here's the deal. If this would have been my graph, like A and B, and I have a flight that happens at 7 in the morning and a flight that happens at 7 at night, we'd have 2 flights that go from Atlanta to Boston. So instead of a 1 here, I'd put a 2. But that's not what it says. And it does say flights, but we're not going to get that technical in it at this point. So, I mean, we're just going to say I have access from Boston to Atlanta and back and forth with a flight, okay? So we're not going to get too crazy with the number of flights and all this. All right, can I go from Boston to Boston? Well, no, technically no, because I can't loop around. It didn't say so. So if you're looking ahead, you might say, well, I'm not going to go from Chicago to Chicago. I'm not going to go from Denver to Denver, Erie to Erie, Fairbanks to Fairbanks, or Greensboro to Greensboro. So if you want to go ahead and put zeros there, you can. And that happens a lot of the time. And again, the exception would be if you have a graph that looks like this, like A loops around to A. Well, then you have one flight that does that. Okay? All right, can I go from Boston to Chicago? No, I cannot. Can I go from Boston to Denver? Yes, I can. Can I go from Boston to Erie? No. Boston to Fairbanks? No. Boston to Greensboro? No. 0 flights, 0 flights, 0 flights. All right. And now at this point, you're like, okay, I get it. So here's what I like to do personally. I like to put 1s where I see flights and then just leave the rest blank and then fill in the zeros later. So I'm going to just go through here and put 1s where I see things. So C to A, yes. C to G, yes. C to F, yes. Those are zeros. We'll take care of it in a minute. All right, D to B, yes. D to G, yes. E to A, yes. F to C, yes. I'm going kind of fast. Feel free to pause the video or go slower or slow the speed down. G to C, G to D, G to C, G to D. Okay, everything else is a 0. So I'm gonna double check and make sure I'm right. And give me a second while I do that. D, that one, that's the thing. E only goes to A, D goes to B and G. Yep, we're good. So we're going to put some zeros. And everything else. And this is the adjacency matrix. It tells us which vertices are adjacent to the other ones. And it not only tells us which ones are, but like how many paths there are in between them, which in this case is just 1, right? So we're not getting too technical. So when it said write the adjacency matrix, that's what happened right here. All right, also, I want to point out adjacency matrices are always square. Always. Number of rows is going to equal the number of columns. In the next video, we will define vertex and edge and all those types of things.